And so what we're trying to investigate is what could happen to bring the giant impactor from some location to the Earth. And as pointed out, that a postdoc here at NASA Ames, and it's supported by Oak Ridge Associated Universities through a contract. So this is go to the setup, the results and conclusions, and if we have time, we'll go back through some other things. So here's a graphic to show you that this is one of the non-canonical ways that you're going to make the moon that Julian's going to talk about, where you take two planets and it goes through this evolution, and that we're trying to do is to do everything to figure out how do you get to this step instead of going through all of this. And the traditional way to do that is you start from post-oligarchic planet formation, but in order to do that, to get to this step, that would take us years to do it. And so we kind of skip ahead and make some basic assumptions so that we don't take years to do something fairly straightforward. And so we assume there's 5 terrestrial planets existing. And so if we're going to do the planetary formations, we go through, make our planets, and select out the ones that look like the solar system. So instead of doing that, we just take the solar system and add another planet, and then we use a conservation angular momentum kind of approximation to say where can we put the small object relative to the big object. And those are going to be our 2 things that we're going to vary and leave Mercury, Venus, and Mars in their present positions and their eccentricities. We're going to assume that the collisions are perfect mergers, so we're only going up to the impact point, and after that we're just looking at angular momentum deficit to see whether it would be stable over long periods of time. And then we look for when the impact occurs, does this make sense what we think about the early solar system? And so we use this 70 to 110 million years after CAIs to say when that's going to happen. And so when we say something at time equals 0, this is around 30 to 50 million years after CAIs, giant impact happens, and the end of our simulation is actually 200 million years after CAIs. And so things that we can vary, one is the mass ratio, because in the giant impact theory, it's a Mars-sized object or larger, and so we don't know how much larger it could be. And so we start with an 8-to-1 mass ratio, which gives us a Mars-sized object for a projectile, a 4-to-1, which is twice the mass of Mars, and the 1-to-1, which is the equal mass progenitors. We investigate 2 different gas giant configurations, one where the gas giants are in their current locations, the other one's with the NESF model, and see if we can get any difference in the results. And so what can happen, we'll divide things into 6 categories, what can happen, and then select out the ones that are most consistent with what we see today in evidence. And so part of this evidence is the timing of the impact, and so we take the 30 to 50 million year range to be when the time which our 5 first planets should have formed, and then the time of giant impact, we take the 70 to 110 million year range, and then we do the angular momentum deficit, which is a comparison of the excitation of the system, and we only expect up to 2 times the current value of A and D. And so an example, these are showing the initial and final states of some systems. And we see that for the most part, Mercury stays where it's supposed to be, even after this 200 million year evolution. Venus stays where it's supposed to be. Mars stays where it's supposed to be. The blue right here is the proto-moon. And then the black ones you can barely see is the proto-Earth. And when they come together, they make the green circles, which would be the Earth-Moon system. And we see that they come together more or less where they're supposed to be. And so this is some of our results. Since if we're doing SPH, it would take a long time to do one simulation. If we're doing planetary growth simulations, it takes a long time to do one simulation. Since we're taking the basic assumptions and trying to do the middle part, we can do a lot of simulations to find out a lot of different outcomes. So in doing this, we did 8,000 different simulations, found out what the outcomes were, put them into our categories, where the ones we're most interested in is success, which is the green stars, which you kind of barely see. But what we do is we take this and do an interpolated map, and so all the green stars are turned into white down at the bottom so they pop out. And this is for the 4-to-1 mass ratio. And so from this, we can see lots of dynamical resonances that form. And also we see that all these points tend to lie on border regions between the red and the blue, where the red is where things happen way too fast based on our timing, and the blue tells us nothing happened at all. And so this is doing the same thing, but using a NESF model. So we can flip back and forth. The thing that we see most differences is on this side, in that the NESF model, a lot of this gets cleaned up. And so we don't see as many type of impacts when we extend to further distances in AU of our source region of our impactor. And so this tells us that this could be a more unique solution using these, or it tells us that we won't expect anything to come out that far. And so that puts another constraint on our velocity distribution. And so doing some statistics on that result, what we do is we try to look at the collision parameter as well as the collision velocity, and we see that a lot of that, if we put it into our AE space, it goes down to the bottom here, and then we see this better in the density plot. That we tend to favor a canonical type collision where it's slow and it's a very oblique angle. And then also we have some boxes that correspond to different impact scenarios where the Chook and Stewart is this gray box. And then some of the other ones, the hit and run is here, and then the Canuck 2012 and Canuck 2004. And because we favor the canonical type impact scenario, we would favor Canuck 2004. This is showing of all our simulations, we plot them versus AMD. This tells us how likely they are to be stable after the impact. And so what we do is we look at the AMD right after. When we say right after, we mean a year after the impact, and then an average over 10 million years. And the thing to see is that of all these blue points, blue and red and green, which are the solar system cases, they all move up over 10 million years in their average. And then all the NESF model ones, which are the yellow dots, will stay below a line of 1. And so if we are going to follow people that use the NESF model, this tells us that we'll get more of those with a lower AMD, so that whenever a NESF model occurs, it will increase the AMD later and then rise up to a level of 1 again. So it gives us kind of a check on the NESF model. Is it giving us a result which it needs to account for later? This is kind of an evolution of AMD if we do the dynamics. And the main point to take away from this is that for the red, which is the solar system giants, the blue is the NESF model, is that the red takes more of a random walk, and it goes up and down quite a bit. Whereas for the NESF model, it's pretty flat, and it has almost a step-like transition after the giant impact. And so to see what should happen, this wants to work. Maybe. Should just be a click on it and it should start. Ah, there it goes. And so this is showing the evolution of one of our cases. And so if nothing really should happen, everything should bob up and down. But we see that, see it better probably on the screen, that the bars on each side is the aphelion and perihelion distances that object has, and when they overlap with each other, it means they're going to have close encounters. And see that these two are having quite a few close encounters, and then actually and the next one we'll see that they switch places until they finally collide, and then down here is plotting the AMD versus time. And so we see that this one had kind of random, the one's right here, and then kind of up and down again, whereas the NESF model was fairly flat, and then the step. And next slide, please. Oh, there should be another one, because I think this is the same one again. Can I get the next slide, please? Oh, there's the next one. And here's one where we start on the other side of where Earth would be. And so this one we watched where the the blue and the green dots are. And we should see that they start switching places until finally there's a giant impact.
2 minutes. All right. Almost done.
So, next slide, please. It keeps restarting the video. Okay, and so this is a graphic showing we take all the results that we did in those two big plots of A and B, and we made a cut to say that what we expect them to be. We find that if we plot them back on AE space, we see all the successes we have fall on these two lines here. And so this leads us to believe that if we were able to go back and say there's a source region for the impactor, it must be near where the Earth formed. And also I want to point out that of the 8-to-1s don't go out as far, the 1-to-1s are all pretty much in line. All the extra ones here are more the NESF models that extend further out. And so what can we say is that the Earth and Theia may have formed closely spaced. This doesn't mean they formed at 1 AU, but whatever they formed at, they will have formed together. And so it may explain, say, that they should be similar in their composition. And it may exclude some of the non-canonical scenarios, is that since ours favors the canonical scenario, and it may say that the Chuck and Stewart model may not be consistent with our simulations. How do we get the impactor from that part of the solar system to the Earth? Well, we use secular interactions because it can't happen that quickly, and there could be resonances that could help along the way. And so for the future evolution, we want to know that will our system survive in the LHB, or will they become dynamically unstable? And this would say, is the NESF model necessary in this regard, or do we need some other model to explain the things that NESF does? And some references, and I'll take questions.
We have time for some questions. I have so in this model, you don't have sort of a disk of planetesimals which is gradually going away. Is that the next step you want to add in?
The next step is we want to add in between 0.02 Earth masses to 0.2 Earth masses of debris, and then we'll evaluate that to see if we can get through the giant impact and get a late veneer, and then go all the way up to NESF model and see if we can get everything that we got before to survive that long. Okay. But as this first step, we needed the baseline, so we did everything without debris first, and it was faster.
Okay. Other questions? Okay. Thank you very much.